Welcome to the channel Physics Made Easy. In the I.SC sample paper, today we will discuss section D. There are 3 questions, each of 5 marks with internal choice. Let us discuss question 20. A part, starting with an expression for refraction at a single spherical surface, obtain lens maker's formula. You know lens, if you represent it like this, one surface of the convex lens, this one, so here it is glass and here it is air. You suppose this is the medium N1 and here since it is glass, then medium N2. What happens for a single surface if you see an object which is supposed to be point object is placed at point O, the ray incident at the lens at this surface. If you draw a normal, that is line joining the center of curvature of this surface and point of incidence, this is center of curvature for this first surface C1 I have written, then this will be the normal. What will be this angle? Angle of incidence. Then in the denser medium, in the glass, the angle of refraction will be less than the angle of incidence, and suppose the final image is obtained here by this first surface is at I dash. So, O object, its image is at I dash. This is the object distance, this is R1. If you write here the distance of this radius of curvature till the point C1, so this is. What is the expression? You know, it is written by N2 upon V minus N1 upon U equal to N2 minus N1 upon R. Learn this relation how to derive using alpha, beta, gamma angles, okay, for the single surface refraction. How to derive this expression? You should know. Here, starting with an expression, it is not said how to you have to derive. Then look here, in place of image distance measured from this point, you will find that this image distance is V dash, as this is the image at I dash. So, you put here dash and U same, and R, R1, so you write here R1. Now, since lens is supposed to be made up of joining another surface, I have shown here curvature. For a thin lens, you have to show very little curvature like this. I am going to show here. Look here, only lesser one is the curvature. Curvature should be very less. Okay. Now, look, if you join another surface, then this side will be glass and here will be air. How will you make it in the same figure? You know the lens is supposed to be made up by joining this, the second surface. Here now this will be the N2 and in this case it will be N1. This I dash will act like the object for this second surface and the final image will be formed at somewhat point I. Okay. So, this will be the distance V for this second surface, and for this second surface here it will be N2, here it will be N1, and the radius of curvature for this second surface will lie on this side. So, suppose at this point this radius of curvature, then you can write it as C2 and this radius of curvature R2. For the second surface, how will you write the relation? Since this ray from O to point, suppose this point is P, is incident ray for the first surface and refracted from P to M. and find this forms the image at I dash. This ray is now on putting the second surface is incident at this surface and it is converged here to find the image, final image of I dash at I. How to write the relation? Just reverse N2 and N1. So how will you write here? This is N1, this is N2, this is equal to N1 minus N2. Right? Then here this is the image distance. What is image distance here? This is V minus this is the object distance. What is object distance for the second surface? This expression we are writing for the second surface. So you will write here this will be V dash and here it is R2. Okay. Now this can be written as N1 upon V minus N2 upon V dash equal to N2 minus N1 upon this minus R2. Can be written or not? These two surfaces are joined to form the lens. So this is expression for first surface, this is for second surface. You will add it. What will you get? This N2 upon V dash, this minus N2 upon V dash will be cancelled. So after addition 1 and 2, what will you get? Take this N1 common. This will be 1 upon V minus 1 upon U equal to N2 minus N1. This will be also common within bracket 1 by R1 minus 1 by R2. Divide it by N1. What will you get here? This will be N2 upon, this will become N2 upon N1 and this will become minus 1. Okay. Whole division by N1. So N2 upon N1 minus N1 upon N1 will become 1. Now if U is infinity, object is at infinity, then V will be F. What can you write here? 1 upon V minus 1 upon U as 1 upon F. If object is at infinity, then image will be at the focus F, V equal to F. So this is the expression which was here, it is said to be derived. This is called lens maker's formula. Why this is called lens maker's formula? Because lens is made by knowing the value of radii of curvatures and refractive indices of the materials in the of the surrounding at the material of which the lens is made. So how much will be the focal length of that lens? So that's why it is used to design the lens. It is called lens maker's formula. Second part, state how will you increase the magnifying power, resolving power of an astronomical telescope. B part, you know, magnifying power of a telescope is given by minus FO upon FE within bracket 1 plus FE upon D. Learn the relations. How will you increase? If you take the objective of large focal length. So what will you answer? To have large magnifying power, objective of large focal length is to be selected. Similarly, resolving power of the telescope is 1d upon 1.22 lambda, where d is the diameter of the objective. So a large objective is taken to collect more and more number of rays to get bright image. So to take large objective, resolving power can be increased. To take objective lens of higher, larger focal length, FO will be larger, then magnifying power can be increased. Look the choice question. In this choice question, first part says in Young's double slit experiment show beta equal to lambda d by d, where the terms have their usual meanings. Beta is fringe width, lambda monochromatic light wavelength, capital D distance between plane of the slit and the screen, and a small d distance between both the coherent sources or the slits. You know, in the Young's experiment, a point monochromatic source from this source two small slits are cut, they are derived in such a way that the point source lies at their bisector. Look here, if this is the source, I am drawing here the bigger one, this one is the first source and this one is the second source. So this distance and this distance is same if this is S1 and this is S2. What happens that at the screen we obtain the fringes, the light is coming from S, but since except these two holes, fine slits S1 and S2, all these portions are opaque. These two are derived from the single monochromatic sources, and this source is situated at the right bisector of them. That means this path length from S to S1 is same as this path length from S to S2, S to this S2. Therefore, these sources produce waves of same phase, and this is the requirement of interference pattern to take place, that S1, S2 act like the coherent sources. What happens at the point C? The light waves coming from S1 and S2, they will travel the same distance, they will meet in phase. Therefore, at point C always maxima will be produced, that is central maxima, because path length is 0, phase difference will be 0. So, this is the condition for maxima. At some other point, suppose at this point P, okay, what happens? Let the ray coming from S1 and S2 meet at this point, forming certain image fringe. So, suppose this is the ray coming from S1 and this one is from S2. There is path difference. How to get this path difference? We draw a normal, that is perpendicular, and if this angle is supposed to be theta, then joining this midpoint O to the point P, if you join this midpoint O to the point P, it is said here that this angle is also theta and here this is theta. Okay, suppose this point you name it M. Then S1, S2 are coherent sources. From these two sources the waves are reaching at point P. They are meeting there to find the fringe. What may be here? This distance of the nth fringe from the central maxima, we can write Yn. Suppose Yn is the distance from central maxima of what? Nth fringe, which is found at point P. Now, since this distance is very large as compared to the distance between S1 and S2, which is very small, shown by small d, wavelength is monochromatic lambda. How to find this expression beta equal to lambda d by d? Look, path difference here at point P reaching at which the waves are reaching from S1 and S2 is be S2P minus S1P. It will be or not? This is S2P and this is S1P. Then difference will be S2M. Will be or not this one? Look, for point P, this S1 and M, they are at the same distance. Also, this path difference is given by n lambda for bright fringes. Learn the condition where n is supposed to be 0, 1, 2, 3 and so on. Also for dark fringes, S2m is n minus half lambda. For what? For dark fringes, where n is 1, 2 onwards, an integer. You have to learn this. Now look here, the triangles. In the triangle S1, S2, M and the triangle OPC, look, they are similar triangle OPC and S1, S2, M. And in the similar triangles, we have assumed here this angle theta and this one is also theta. Ratio of the same sides can be taken in the similar triangle. Look here, if you take here this, in this triangle, you can write here this S2m upon S1, S2. Okay, S1, S2m triangle. Then what will you write here? This, in this triangle OPC, what will you write here? You will write here this PC, that is, I am writing here, okay, first PC upon this triangle, this distance OC, I am writing here S1, S2, okay, you can write here PO. First of all, I am writing OP, but since we will suppose OP as same as OC, that is equal to D. Then what will you write here? This S2m, what is this S1, S2, D, what is this PC, YN, and what is this OP? This is here, this OP or PC, this is D. Okay, now let us suppose at point P bright fringe is obtained. So for bright fringes, what will you write here? For bright fringes, let us suppose n lambda is d yn upon d, therefore yn will be dn lambda upon small d. If at point P bright fringe is obtained, then next bright fringe, what will you write? This is the nth bright fringe. For next bright fringe, in place of n, you will write n plus 1. So this is the expression number 1 for next bright fringe. Next bright fringe, you will write yn plus 1 equal to d lambda n plus 1 upon d. This is the expression number 2. For nth to n plus 1 bright fringe, you know, in the interference fringes of equal width and alternate bright dark fringes are obtained. So from n to n plus 1th, 2 bright fringes, in between 2 successive bright fringe there will be 1 dark fringe. So if you subtract this distance yn plus 1 minus yn, that is, you are getting the fringe width of dark fringe. Okay, that is of dark fringe. So if you subtract equation 1 from equation 2, what will you get? This beta will be the fringe width of darker fringe. Then look here, this beta, what will you get? If you subtract these two, this d lambda upon d. In the same way, you can also prove that, let us, this yn is the distance of dark fringe, then in place of n, what will you write? N minus half. What will be the distance of next dark fringe? Then you will write n plus 1, then again minus half. Subtract, you will get the width of bright fringe and it will be same d lambda by d. Okay, I hope it will be clear. In the part B, show graphically how intensity of fringes varies in Fraunhofer diffraction. In Fraunhofer diffraction, we get the fringe pattern like this. How to show it? You mark the points at straight line at equal distances, and in Fraunhofer diffraction, central maximum width is twice of other secondary maximum and of the largest intensity. Suppose if this is the intensity axis here at the, we should write here this I, and this is the angular fringe separation. Okay, then how will you find the graph? If you see that this is the total fringe width of the central maxima, you would draw the, this is the fringe width, then you find the, this is shown by principal maximum, okay, and its highest intensity. The secondary maxima is of this intensity, then next one is of lesser intensity of the same width, and these secondary, first secondary maxima, second secondary maxima, then third secondary maxima, they have intensity decreasing. They are of same width but decreasing intensity. Similarly on this side also, draw the identical patterns and of the falling intensity. What is this point? This is minus lambda by A, this is plus lambda by A. What is the width of central maxima? 2 lambda by A. Okay. Now this is the secondary maximum. So in this way this pattern is shown, and you have to show the graph Fraunhofer diffraction pattern intensity variation like this.